Sound waves, like any waves, can be made to exhibit interference. Whereas a material object like a rock can't share its own space with another rock, more than one vibration or wave can exist at the same time in the same space. Drop pebbles in water and the waves produced by each overlap and form interference patterns. When more than one wave occupies the same space in the same time, the displacements add at every point. This is the superposition principle. Here's a diagram of a pair of waves that superimpose. When the crest of one wave overlaps the crest of another, their individual effects add to produce a wave of increased amplitude. These waves are in step. We say they're in phase. For identical waves, the resulting amplitude is twice as great. We call this constructive interference. When the crest of one wave overlaps the trough of another, we say they are out of phase. Their individual effects are reduced because the high part of one wave fills in the low part of another. For identical waves out of phase, as we see here, cancellation occurs. The result is zero amplitude. This is called destructive interference. Wavy Wilma shakes the free end of a rope that is tied to a wall and produces the pulse of a wave. The wall is too rigid to shake, so the pulse reflects back along the rope. If Wilma shakes the rope just right, she can cause interference of the incident and reflected waves and form a standing wave. Here Wilma shakes the rope until she sets up a standing wave of one segment. When she shakes with twice the frequency, she produces a wave with two segments. This is a standing wave of one wavelength. When Wilma shakes with 3 times the frequency, she produces 3 segments. The standing wave she creates is of 1.5 wavelengths. Standing waves are set up on the strings of a musical instrument when struck. Here nephew John sets up standing waves with his guitar. And granddaughter Gracie produces soothing tones with her clarinet. You can set up standing waves the next time you're taking a bath. Slosh the water back and forth with just the right frequency and you produce a standing wave. Yum, bathroom physics. Standing waves can be produced with either transverse or longitudinal waves. Here we see a comparison of both types of waves. In either case, when the crests of one wave overlap the crests of another wave, increased amplitude results. Or when the crest of one wave overlaps the trough of another wave, decreased amplitude results. In the case of sound, the crest of a wave corresponds to a compression, and the trough of a wave corresponds to a rarefaction. Interference occurs for all waves, both transverse and longitudinal. Maybe click on the pause and take a few moments to study this. Sound interference is dramatically illustrated when monaural sound is played by stereo speakers that are out of phase. Try this demo and amaze your friends. To put your speakers out of phase, simply interchange the input wires to one speaker, that's positive and negative wire inputs, reversed. Then for a monaural signal, when one speaker sends a compression of sound, the other sends a rarefaction. The resulting sound is not as full and not as loud as from speakers properly connected in phase. That's because longer waves are being canceled by interference. Shorter waves are canceled as the speakers are brought closer together. And when the pair of speakers is brought face to face against each other, very little sound is heard. Only the sound waves having the highest frequencies survive cancellation. You must try this to appreciate it. It's yum. Destructive sound interference is a useful property in anti-noise technology. Such noisy devices as jackhammers are now equipped with microphones that send the sound of the device to electronic microchips, which create mirror image wave patterns of the sound signals fed to the operator's earphones. Sound compressions or rarefactions from the hammer are canceled by mirror image rarefactions or compressions in the earphones. The combination of signals cancels the jackhammer noise. Noise-canceling earphones have been common for pilots for several years, as Ken Ford testifies. The cabins of many airplanes are now quieted with anti-noise technology. When they're not, that's when you should wear your noise-canceling earphones. When two tones of slightly different frequency are sounded together, a fluctuation in the loudness of the sound is heard. This periodic variation in the loudness of sound is called beats and is due to interference. The sound from two slightly mismatched tuning forks is momentarily in step, then out of step, then in again, and so on. When the combined waves reach our ears in step, say when compressions from one fork overlap those of the other, the sound is maximum. A moment later, when a compression from one fork meets up with a rarefaction from the other, the sound's a minimum. Hence, the sound that reaches our ears throbs between maximum and minimum loudness, and we have beats. If we overlap two combs with different teeth spacings, we'll see a moire pattern that is related to beats. The number of beats per length will equal the difference in the number of teeth per length for the two combs. Beats occur with any kind of wave and provide a practical way to compare frequencies. To tune a piano tuner listens for beats produced between a standard frequency and the frequency of a particular string on the piano. When the frequencies are identical, the beats disappear. Beats can help you tune a variety of musical instruments. Simply listen for beats between the tone of your instrument and a standard tone produced by a piano or some other instrument. Dolphins use beats in surveying the motions of things around them. When a dolphin sends out sound signals, beats may be produced when the echoes it receives interfere with the sound it sends, sort of like when Wavy Wilma shook her rope against the wall. When there's no relative motion between the dolphin and the object returning the sound, no beats occur. But when there's relative motion, the echo has a shift in frequency and beats are produced. The same principle is applied by radar guns used by police officers. The beats between the signal that is sent and the one that is reflected are used to determine the speed of a car. Interference, a property of all kinds of waves, is fascinating. Speaking of all kinds of waves, I want to leave you with a question. Suppose a friend asks you if a radio wave is a high-frequency sound wave. What is your answer? Until next time, good energy.